So thanks very much for the invitation. This is not quite my usual audience, but feel free to sort of stop me if I say something that's not clear to anyone at any point in time. And as I said, this is not what I normally talk about. So as Brad said, my day job is an astrophysicist, not a chapel code writer. I specialize in cosmology, and if that doesn't immediately make sense to you, it'll hopefully make a little bit more sense by the end of my talk. I am a chapel enthusiast, and I'll give you my version of how I got into chapel. I sort of bumped into chapel early in its public existence, and probably around like 1.05 or something like that. I saw some blog post about this. I like programming languages, which is, I'll try anything out for a week and see whether I enjoy playing with it. And I think I tried out chapel at that point in time. It looked all fun, and then nothing quite worked beyond the simple first few things. And I said, okay, fine, and moved back on to my usual day job. But I was intrigued enough, as I said, intrigued but not compelled. And then this entire interaction with Brad occurred, which is, I sort of came back and looked at chapel. Maybe, I can't remember, it was 1.10 or 1.09. The language looked a lot more polished and stable. And I happened to be in Seattle for a meeting, and I said, you have an hour free, so you say, okay, can I just walk down to the Cray offices? And partially intrigued by, where are the Cray offices? I've been using Cray machines. It's like, what do these offices look like? We met up, and I think we talked for about 2 hours that day, chatted about things. And I think the immediate thing that came out of that, I sort of said, we were trying to discuss what things would you really like to have in chapel, and I said, look, I use FFTW all of the time because I always want FFTs. Can chapel call into FFTW? And that's where the FFTW module in chapel came out of, sort of that interaction with Brad and sort of a few months' worth of work around there. I've used chapel in one use case to date, and I'll give you a flavor of where that use case came in. It's a pretty simple use case, but it's a case which has actually gotten used in something outside of, in a paper that actually got published. So that's nice. And chapel, I think, got a acknowledgement in that paper, so you guys should be happy. What I'm going to show today is a couple of proof of principle applications. So I'm not going to walk you through sort of the boring parts of how these things get used, but at least give you a sense of the kinds of calculations that I do and why I'm intrigued by chapel. And I'll try to make an argument that 1.13 plus, sort of what will go presumably into 1.14, has most of the bits that I need. And so that I'm personally hoping to use it a little bit more broadly. We've been talking a lot about performance, and I wanted to make a different point out here, which is that performance is important to me, but so is the ease of prototyping new ideas. I'm fine with taking a factor of 2 hit over someone who spent 4 years working on a problem and tuning everything out of it. Because quite frankly, I don't want to spend 2 years on this problem. I want to write the paper on it and move on. And a factor of 2 hit is perfectly fine with me. In particular, absolute wall time does matter in some sense for me, which is the distinction between a minute versus a second versus a millisecond quite often doesn't actually affect my life because I can't think anywhere near that fast. So as long as the computer has the answer faster than I need the answer from the computer, it's good enough for me to do a lot of what I care about doing. And so there's a lot where you can sort of say, oh, well, I was not going to get a factor of 2 hit performance gain, because quite frankly, even if I wrote this in C, I was never going to get that factor of 2 performance gain because I'm not a good enough programmer to write all of those optimizations down. I've got better things to do with sort of my time to go to the answer. And sometimes it does. But sometimes, and there are cases where it does matter. And so in those cases, it's nice to find the slow steps to optimize. And that's the theme that's going to keep coming up in what I'm going to show is, for me, it's easiest. An interesting language is one where I can prototype quickly, scale up to a large number of machines, not necessarily running with the machines running anywhere near peak performance. I'm not worried about that. But my job's running faster. My job's roughly scaling the way I would expect it to scale. If I ran it on 10 cores, it ran roughly 10 times faster. That 10 was 5. I'm not going to lose a whole lot of sleep about it, because that's still a lot faster than it would run. That's good enough for me in lots of cases. I should sort of say, what do I normally use? And it's only, normally some combination of that set of languages out there. Mathematica is great for sort of doing symbolic stuff, but not anything else. And it's sort of C++ and Python. I'll show you. I'll make the arguments why I like C++ and Python, and why I don't like C++ and Python, and where I think Chapel can fill in the things that I don't like about it. I should also, please feel free to interrupt at any sort of point in time. If I say something that's not, that you disagree, or if you violently disagree with me. A couple of warnings. As I said, this is not my usual audience. I'm not a CS person, so please expect to see non-optimal code. Don't hold me to poorly formatted code if I've not commented things properly, or my variable names are X, XX, and XXX. That's just life. I try to write sort of decent code, but it's never going to be clean. These slides haven't been vetted by Chapel, the Chapel team. They've helped in lots of the Chapel code that I've written, and those are at least 3 names of people who've had emails from me saying, I didn't get this to work, why? And they've sent me long, detailed explanations. So all of the mistakes here are all mine. The slow code, if I claim some code is particularly slow, that may or may not be Chapel's fault. It could also be my fault. I did something stupid. If I did something stupid, please let me know, because then I will fix that with something that I do. And as I said, not my usual pattern, so apologies in advance for some glitches. So I want to do 3 things today. I want to give you a little bit of a flavor of the science that I do to just motivate why I'm interested in Chapel. So that's going to be the cosmology part of this talk. I'll then spend some time giving you at least 1 or 2 sort of the proof of principle examples. And this is sort of, here's an application. It's not a complete application, but it's close to the kinds of things that I would want Chapel to be able to do. And then I'll talk a little bit about sort of my adventures with sort of writing code in Chapel and sort of checking back into the Chapel branch. And we'll see all 3 of those cases as we go along. So with all stories, you have to start a story somewhere. And so my story starts, as pretty much every story in physics starts, with Einstein, not his theory of special relativity, but his theory of general relativity. So Einstein writes down the theory of general relativity, explaining all of gravity. And one of the first things that happens with this theory is people start to ask, well, how can you explain the universe with this? So people start writing down models. Very much soon after Einstein writes down his equations of general relativity. And one of the first things they noticed with this is they say, one of the first consequences of those equations they wrote down was that the universe expands. So the first prediction, there was a prediction at that point in time of people, was that the universe should naturally be an expanding universe out here. Now, at this point in time, no one had ever measured the expansion rate of the universe. And we said the universe was expanding today. Lots of people have heard about the expanding universe. Back in the 1960s, no one had sort of talked about expanding universes. And so the idea of an expanding universe was a surprise. And so Einstein immediately said he needed to fix this problem. And he fixes this problem by adding in a term into his equations that basically turns off the expansion of the universe. And this term becomes important because it'll come back out here, but he turns off this expansion rate of the universe. So that's the first part of the story. This is in the early 1960s, and then the second part of the story is the discovery of the expansion of the universe, which is by this gentleman, Edwin Hubble, using this telescope out in Mount Wilson. It's a 100-inch telescope, and he basically noticed that things further away were moving away faster. So this is the so-called Hubble's law. And the natural explanation from this was that we live in an expanding universe. And Einstein puts 2 and 2 together and realizes that his original theory actually predicted this, and he sort of goes back to this and sort of calls this his biggest blunder. He introduced these additional terms. Those are not the terms that are written on the blackboard, but I can never find an equation that had him writing the right equations on the blackboard. But he says, this introduction of this term that made the universe static was, of course, a big mistake. Okay? So that was the start of the story. And then we sort of built up this picture of our universe. We sort of live in this expanding universe out here. Now, I want to do a thought experiment, which is, what would an expanding universe, so I say, let's go beyond an expanding universe. It's expanding. What's the rate of expansion of that universe? And let's do the thought experiment of what we would expect gravity to have. If you have just take the gravity that we know. So if I take a ball and I throw it off the surface of the Earth, it goes up to a certain height, slows down, and stops. If I throw it fast enough, it'll keep going in forever and ever up to the so-called escape velocity. That's how we get satellites out of the Earth. But in all cases, it's slowing down. The ball is always going to be slowing down. And that's not surprising. Gravity is an attractive force. So if I did the same thing with the universe has still got gravity working inside of it. And so there's an attractive force out here, and I would expect the universe, the expansion rate, to slow down. Gravity should slow things down with time. And so people said, let's go out and measure this expansion rate, the slowing down of the expansion rate, because it gives you a way of telling you how much matter there is in the universe. I could weigh the Earth, for instance, if I could throw a ball up with a known speed, I could tell you exactly, if you saw when it stopped and turned around, that would tell you exactly how much weight the Earth had. So it would be a complicated way of weighing the Earth, but it's no harder in some sense than weighing the Earth by saying, let's look at a satellite going around and measuring what its speed is. The satellite's really just falling around. So people started to go and do this experiment, and there was a big surprise when they tried to go and do this experiment, which was that the universe wasn't slowing down as you would expect, but the expansion rate seemed to be speeding up. And the way they detected this is an interesting way. It'll play a little bit into our story, which is they said, let's look at a particular type of supernovae. A supernova is a star that explodes. There's a particular class of supernovae that basically has the same luminosity. And I'm glossing over a technicality out here. They don't quite have the same luminosity. They come with a little thing, a sign in them that says, this is the brightness of the supernova. So you go to a hardware store and you buy a 100-watt light bulb, you know what the wattage of that light bulb is. So the supernovae come with little signs on them in their packaging that says, this is a 100-watt supernova, this is a 50-watt supernova, and so on. But you know the brightness of the supernova. Now, if I took a bunch of these light bulbs and I put them at different distances from us, and I look at how much light I get, I can tell you how far the light bulb is. So a simple way of telling you how far things are. Things that are further away have less light coming to you. So people started to use these supernovae, and you start going further and further back in time and trying to map out what the expansion rate of the universe is doing as a function of time. And the big surprise they found was that the supernovae looked like they were dimmer than you would have expected with an expansion rate that was slowing down. And the only way to reconcile this, and there's lots of checks and balances that go into all of these things, but the only way, even from just a simple intuition out here, this is an incredibly surprising result because gravity was attractive. There's nothing in that picture which would give me something that was repulsive and would cause something to accelerate away. To accelerate away, I need to sort of push on it and push it outwards. And gravity can't do that naturally. Okay, so this was the big surprise, and this got the Nobel Prize. Oh, I lost that slide. I didn't mean to go with that. All right. There was the Nobel Prize this was done in 1998. So not very long ago. So these are relatively new developments in cosmology, and it got the Nobel Prize in 2011 or 12. Can't quite remember when. This is something now that is in our standard canon of what we think the universe looks like. So here's a picture of what the universe looks like from sort of start to finish. NASA makes these wonderful images for every one of its satellites. This was for the Wilkinson microwave anisotropy probe, which flew about 15 years ago now. And there's an initial stage of the universe, and I can spend an entire lecture talking about this, but this is not the place to do that. There's the formation of the first galaxies, planets, the solar system, you and I, and then you get to this period of the so-called dark energy or this accelerated expansion. And people use dark energy. Dark energy is our placeholder for our ignorance. It's what sort of causes this accelerated expansion of the universe. So what I do is, one of the things that I'm interested in is trying to say, this is something that's clearly either some new form of matter or energy in the universe that's causing this, or it's a breakdown in general relativity. And both of those are interesting statements from a physicist's point of view. It doesn't really matter what the correct answer is. Each of those answers is an interesting answer. And we'd like to know what the correct answer is, of course. But we're sort of guaranteed, if we can figure this out, to be wiser than we were when we started off. So what I'm interested in doing is saying, what are the different ways of going after this dark energy and mapping out this accelerated expansion? And the way I do this is by basically making maps of the universe. Here's a map of the universe. So the universe is known in the 15th century. Basically, the universe is described by Ptolemy. This is a map of the world, and lots of things around here that are presumably causing physical features in the world out here. But this is the reason we make maps in some sense. It tells us what's around us, and then we can go a step from those maps away and try to learn something about the physics that's going on. And so this is what we're trying to do, except we're trying to build maps a little less local than this one. We're trying to make maps of what the galaxies around us look like. So we're in the center of this picture out here, and there are two sort of pie slices out here. We like talking about these as pie slices. And here are a whole bunch of different galaxies, all different. Each point in this figure is a galaxy. And so you can see the sort of structure in this. We sort of call this the cosmic web, because this sort of looks like a web-like structure that goes through all of this. And my goal, one of the things that I'm interested in, is understanding how you can use this to learn something about dark energy. And let me give you a one-sentence version of why this might tell me something about what dark energy is. And so the one-sentence version of this, or maybe a few-sentence version of this, is you have to ask, how does this form? All of these structures are forming because of gravity. Things are falling in and forming structures. If I live in an expanding universe, I've got two competing effects. I've got the expansion of the universe, which really doesn't want things to fall into one another, and I've got gravity, which is causing these things to form into one another. So I've really got this competition, and depending on which one wins, I either form stuff, more stuff, or less stuff. And so by actually looking at all of the structure out here, I can learn something about what the expansion rate of the universe is and how much matter there is in the universe, how much dark energy there is in the universe. And I'm happy to sort of go into lots more detail in a coffee break, and I can give you a lot more about this. But really, we're trying to make these maps of the universe. So I thought I'd give you a little bit of a flavor. Let me skip this, and I'll give you a little bit of flavor of how we make these maps. So we start off by saying we want to make one of these surveys. We call these galaxy surveys. We say we're going to do this, so we say the first thing we do is we make a big image of the sky. And so you may take a telescope like this. This is the Sloan Digital Sky Survey telescope. This is out at Apache Point in New Mexico. White Sands National Monument and Missile Range is sort of out beyond there, out here. This is a small, relatively small telescope. It's a 2.5 meter diameter. The mirror is a 2.5 meter diameter telescope, but it was designed and optimized to build big surveys of the sky. And so you can survey the sky and make maps of this, and it looks a lot better on my screen. It looks a lot better if you can sort of zoom it in a dark room. But you can make a map of the sky that looks like this. And there are order of billion objects in the full map that we made of the sky, and we covered about a third of the sky, about somewhere between a third or a quarter of the sky over the years that we've imaged the sky out here. We then select, off these objects, we select about 1 million or 1.5 million of these objects. So we have various selection criteria where we can decide which ones we want to select objects out here. And then we go out and we drill a plate for every pointed patch in sky. So we break the sky up into a bunch of patches. We take a plate, a big metal plate like this one. I've got one in my office. If anyone of you ever end up in New Haven, come by and I can show you what one of these plates looks like. And there are 1,000 holes in this plate, each corresponding to the position of 1,000 galaxies. And I can go and put an optical fiber in each one of those holes and get a spectrum for each one of these galaxies. So here's what we do: is we've got a plate out here, and you've got 1,000 optical fibers coming in out here. Plug that at the back end of the telescope. Light comes in out here, and you go out and you get, for every object, you get a whole bunch of spectra. Each spectrum I can now convert to a distance to a galaxy. So now, if you think about what's going on out here, I've made a map on the sky, so I know which direction every galaxy is, and I can convert these spectra into how far the galaxy is away from me. And so if you go back, think back to that plot that I had, just going to take a few seconds to get back to plot like this. This is sort of a radial distance. So this is in some sense a small sliver of the sky, but a long radial distance away from you. So that's what we're making these maps of the universe. And so we build up these maps of the universe this way, and now we get we can put this all into a box, And there's the box out here, and this is where all the galaxies are. And I just showed you a cross-section. The previous figure just showed you a cross-section. Just a point of curiosity, for those 1,000 optical fibers, you can ask, how did those fibers end up in the holes? Someone actually plugged a fiber into each one of those holes. So over the course of these surveys, someone plugged in 1.5 million objects. It turned out to be the most efficient way to do things. We've got better ways of doing it now, but as of 2012, that was sort of the best way we could do it. Okay, so once we've done this, the real question is, what kinds of calculations do I do with those maps? And so this is where we're starting to start thinking about Chapel a little bit. And so let me highlight another point here that this is going to come back, and we'll talk about it some more. But I've got these maps of the universe. Quite often the question that I'm trying to understand, the question that I'm sort of trying to write code is, the question here is not a question of implementing an algorithm, of saying, I know I want to do this, I now have to find the most efficient way of doing this on the data. Most of the time, the real question is, what question do I want to ask off the data? And how am I going to do that? And that sort of changes the way you think about what you want out of your programming language. I'm less, this is why I keep saying I'm less worried about sort of exact degrees getting the maximum performance, because quite often I could get the maximum performance out of a particular algorithm and then decide 5 minutes later that that was not the algorithm that I needed to be running. I needed to be asking a completely different question. And spending a year optimizing the algorithm for the wrong question doesn't buy me anything. So the kinds of computations we do in cosmology I'm going to give you, these are not the only ones, but I'm going to give you a flavor of the kinds of things we do. We do things where we try to simulate what gravity would do and how all of those structures would form. And we've gotten very, very far. And for those of you who went to Katrin Heitmann's talk yesterday, this was all about how do you build these very, very large-scale simulations of the universe. And in particular here, this is one case where performance absolutely matters, because we want to run the biggest possible simulation so we can get the largest volumes of the universe that we can at the highest, with the largest number of particles, so we can sort of map out the structure in the highest degree of fidelity. So here's clearly a case where performance does matter. We know what problem we're solving, and now you sort of want to just optimize the performance out here. But the kinds of problems I'm interested in, performance matters less. The kinds of things I'm interested in, if we look at this distribution of galaxies, I want to understand, for instance, how do I characterize this distribution? What statistical methods can I use to characterize this distribution out here? This looks like a random distribution. It's got structure in it, but it's still random. And that's true. The initial conditions of the universe were random. We live in a particular realization out of an ensemble of different universes. And so the initial conditions are some random things. So I want to characterize the statistics out of this. I want to say, for instance, if I'm a galaxy, what's the probability that I will find another galaxy away from me? That's what I call a two-point correlation function. I can do n-point correlation functions where I do two galaxies at some 2 points of a triangle away from me, and then I say, given the shape of that triangle. Or I may want to find groups of galaxies or clusters of galaxies and things like that. And a lot of these algorithms, if you want to think about the kind of calculation we're doing calculations that are basically analogous to the simplest Endbody calculation, where you're looping over pairs of galaxies, a 2-point correlation function. You're basically looping over pairs of galaxies and computing distances between each one of those galaxies. And that's what you're going to do. That's what exactly you would do with an Endbody code, except at the end of the day, you don't calculate a force, you want to do something else with it. And so the kinds of operations you want to do efficiently are those same operations. The kinds of optimizations you look for are the same optimizations there. Another class of calculations we end up doing a lot of are things that basically look like something like a potential calculation or a force calculation, which is basically we're solving variance in the Poisson equation. Not always solving. Sometimes we're actually solving the Poisson equation. Sometimes we're solving the Poisson equation with a few other terms added on out here. This is the place where we use FFTs a whole lot. This is where I'll show one of the reasons I've gotten interested. We've been thinking about we use multigrid methods a bunch to solve some of these cases out here. And then the final piece is, I've got all of these operations. I end up doing this over very large numbers of simulations. And it's important to realize why we do this over a large number of simulations. It's because we've got just a random realization of all possible universes, and so my theory predicts the average quantity, but I just see one realization. If I want to say, does my theory agree with the data, I need to know more than just the single average. I need to know what the full distribution is. And so I have to repeat all of these calculations over simulations of these galaxies, simulations that come from things like this, many, many times. This is an embarrassingly parallel problem in some ways. The particular calculation here may not be very parallel, but I have to repeat it over and over again, and this tends to be embarrassingly parallel. And this is one of the reasons that I'm attracted to a language like CHIUW. It allows me to do some of these things where I can sort of mix complicated calculations and still spread them out over n machines very, very fast and very easily without huge amounts of overhead out there. So why CHIUW and not something else? So there are a bunch of languages that I've used in different places. Python, I love Python and it works wonderfully when you're doing a task that someone has optimized and gotten the best code out of it. Basically wrapped C code and told you, if you do this, I can do it really, really fast because I'm going to call the C end out here. If you do that, it works really well, and if you don't do that, it doesn't work well at all, and you can take very large hits out here. It's got a wonderful ecosystem and lots of users, and so basically it's code to do everything you might imagine. You know, you can read every file format you can certainly imagine getting from people. One of the things I dislike about Python, or coding in Python, is quite often forces you to use very unnatural idioms for code. There are cases where a for loop is the right answer, and Python will force you into using things that are not for loops, for instance, and doing more complicated things, mostly because the C, you want to use the NumPy routines out here, which you want to be calling into the C. And so you're forced into things, and you're forced to using more memory than you need, or creating temporaries around everywhere else. I do a lot in C and MPI, and I will say that C++ 11 and 14 are much nicer languages to learn than when I started writing code in C, and so things have gotten really nice. You certainly can reason about performance. There's lots of good tooling about it. OpenMP and MPI are well established, and by what that means is, since I'm not doing anything hugely complicated most of the time, I can find the answer by just going to Google and saying, how do I do this in OpenMP and MPI? I'll get 4 things and detailed explanations about it. MPI is still large, and I really do miss native multidimensional array support in C and C++. It's just something that's sad that we don't have. So what was the things that I liked about CHIUW? The promise of easy abstractions for parallelism was very, very attractive to me. And as I said, a lot of what we do, we will be doing things that are sort of easily parallelizable, but still require a little bit of fiddling around. So you want easy abstractions for that. There was a promise of performance, and so that I could write code that was as performant in C and C++ code. And I have to say, domains are great. A lot of things, the fact that I can express array bounds and index sets, and I can set those index sets to vary in funny ways and stuff like that, it's just really nice. Because lots of computational things you can write much more naturally out there. So what I'm going to show you is I'm going to show you some codes that are written in Python. So here's the code part of the thing. So this is where I run the risk of embarrassing myself. I'm going to show you a couple of bits of code. Some of these are things that I've written just as demonstrations of that I can do them in CHIUW and how well they would work, but also because they were useful to me out here. So I'm going to walk you through a simple Endbody code, just basically doing the sorts of simulations that would run out here. This is a toy problem in the sense that there are way more efficient algorithms and accurate algorithms than the one I'm going to show you, the bits that I'm going to show you out here. But a lot of the pieces are the kinds of pieces that I end up using over and over again. And so a particle mesh code has particles and a mesh. The particles basically are used to track the distribution of matter. They evolve under gravity. The mesh is used to basically accelerate the gravity calculation. So you don't do an Endbody code by just summing over all of the particles. You put the particles onto a grid. You solve Poisson's equation. Poisson's equation gives you the force. But FFTs are much faster than anything else in the world, and so you can basically do this calculation much, much faster than you would by doing a straight n-squared operation out here. And effectively, for all of these codes, this is a thin wrapper around whatever FFT routine you have for your machine, and in this case, it will be a thin wrapper around FFTW. So I'm going to be calling FFTW more and more as often as I can get away with it. So I'm going to show you little bits of this code in CHIUW. And highlighting the things that I sort of find very attractive about CHIUW. The first one is setup. And this is one that seems a little crazy that, this is something that I find attractive about it. But config parameters are just wonderful things. When you're writing a prototyping code, you don't want to write all of the stuff that reads in a parameter file and parses the parameter file, gets all of the bits of information. I want to define a global variable, which is a constant that says this is the size of the object. And I'd love to then be able to say, oh, I want to change this and run this around. And I can't do that in C, and I can't do that in pretty much any compiled language. And I love the fact that in Chapel I can add in a config. And now it's a parameter that Chapel will happily take in at the command line, and I get a code that sort of scales out without me having to write any of the sort of normal parameter handling cases. So that's one thing that I really do like about it. We've discussed, Brad and I have discussed the last time we chatted about sort of reproducibility, saving all of these config parameters so that a user can then say, I know exactly how the code was run, so I can rerun it exactly the same way. It's kind of a nice thing which you would have for some of these codes. Domains are really, really expressive. So the other piece here in this code is the domain for the box that you have out here. For instance, so here's the domain for the box in this case. This is the full box. The box is an n by n by n box. It's an n cubed box out here. There's this weird looking algebra that I do out here. You can ask why I do it this way. It's just because FFTW likes me writing things out in this funny way. This is really the fact that the FFTW requires 2 extra elements to store complex numbers. If you want to do an in-place real transform, you can't quite do that in exactly the same amount of memory and not drive everyone up the wall with a crazy storage algorithm. So this is what FFTW does, and basically I don't rewrite the FFT algorithm, so I'll do whatever they tell me to do. So this is what it is, and then I can tell you where all the real parts are in FFTW. This is where, in configuration space, before I do the Fourier transform, this is where all the data must live, and so the Chapel just lets me say I can slice this out in this a very simple way, and I don't have to worry about did I get all my bounds right, did I copy things over. The dots basically handle that, and I just have to truncate this and say, oh, I only care about the first n elements out of that. And now when I do the Fourier transform, the real and imaginary parts get interleaved with one another, and so I have to deal with that. That's a pain in the neck all the time, except not in this case because I can just do dot, 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 and I step by 2, and I step by 2 with a step off of 1 out there. That basically gets me the real and imaginary parts, and I have a straight indexing into the real and imaginary parts of the array without doing any large amount of work, and I can now just loop over all of these things very, very quickly. So that's kind of nice. And I can talk about where the frequencies are in this space and box and things like that. So I can write index sets for all of these things, and they cost me no memory. So that's also very nice. Okay, I can do things like grid deposition, and there's 2 points I want to make out here. I've got all these particles, I've got to put them onto a grid. This is one of those things where I never have thought of a very clever way to do this in parallel. Because every particle might do, multiple particles might deposit into the same grid point. So the version that I did out here is I used Chapel's atomic support, and I wrote everything down into a grid. This is doing a so-called CIC deposition, so every particle could deposit into 8 possible grid points around you. You sort of look for the closest one, and then you go with everyone around that box, and you work out all of the various differences. It's not much different, very different from the code that you would write in C or C++, except that I have multi-dimensional arrays. And so if I show this code, for instance, to a student of mine who has not been spent years staring at sort of the normal conversions of C indexing into sort of multi-dimensional arrays, they can immediately see what array I've written things down into. And I can also just look at this code and say, did I do it right? The percent ends here are to handle periodic boundary conditions. And I can do that relatively easily. I'll show some stuff that Ben sort of taught me all about stencil distributions and stuff that you can do with that. I can now do things like velocity updates. And so here's my handwritten equations and what you do for a velocity update. You take a potential, you take its gradient, which in Fourier spaces you take the potential and you multiply by I. So you basically swap the real and imaginary parts with a minus sign out here. And this is again, now the fact that I could write down the real and imaginary parts and loop over things in nice ways. I dropped a factor of k. There's a k out here. I'll fix that when I fix these slides. But there's an additional factor of k. I can loop over the real and imaginary parts of the potential and the sort of displacement of the acceleration field, how much I have to nudge my velocity when I do a step forward. So this is just the force calculation. This calculates the acceleration, and then I have to nudge my galaxy. But again, these are very simple operations to do. Firstly, I'm not doing 3 loops that are all sort of wrapped into one another. I'm just looping over all of the indices. The index sets handle all of that. and they handle separating out the real parts of the imaginary parts and things like that. So I can immediately write reals into imaginaries, and I know exactly what's going where. So that's kind of nice, and then I can pull things back out, and then I can of course do things in parallel with sort of one-liners like this, which I quite like, which is you say I need to add to the velocity and acceleration term, and I need to do this in 3 dimensions, but this can clearly happen in parallel because now I have a complete just delta V calculated for everything out here, and so please go ahead and do that for me now in one step. And the only reason I haven't written down this as a single array operation is I need to pick out just one, I'm moving it, I have to, the velocity is a vector, and so I have to do this in each dimension each time around, and so I have to tell you which dimension I'm going through, and so that just tells me how to do that. Okay? And so you can do things like this. This was, from my perspective, this code looks very much like the algorithm that I would write down, and I would basically code this up in exactly that way, and that's useful. Here's another example that I got intrigued by, and so there's a little bit of backstory here, which was I was trying to teach myself how multigrid algorithms work. So you said, okay, I'm going to code down multigrid algorithms. And you say, okay, fine, I'm going to do this, and I may as well try to do this in Chapel, because Chapel sounds like the right language to do it in. It's got grids and stuff like that. And I started coding them down, and then Brad chatted with Brad about multigrid in Chapel, and he pointed me to their attempt to do the NAS multigrid benchmark. And I said, okay, let's try to code up the NAS multigrid benchmark in Chapel. So this is all just stencil operations. And so here's the sort of simplest version of a stencil operation, and you're basically doing something that I would write down naturally, which is sort of doing a for loop over all of the elements of the stencil, and with a little bit of cleverness on how you sort of get at all the various points. This is basically the simplest for loop on over a stencil. Now, of course, there's a story here, which is this was very elegant. The first time we ran this, and I'm not going to show real timing numbers out here. But the first time we ran this, it was slow. And by slow, I mean greater than 10 times the benchmark. I think the first time we ran it was at 60 times slower than the benchmark. The benchmark being just a straight Fortran version of this code. That was not great. So you say, okay, I've argued to you that I don't care about performance, but when it gets to 60 times slower, it really does upset me a little bit. And so you say, okay, I'm going to stay up a little bit late night and try to clean up that code and try to do things better. So you write code like looks more like this. And the nice part is you can get to within about a factor of 3 of the benchmark. Or I could get to within about a factor of 3 of the benchmark by just writing Chapel code. This looks significantly more ugly. It's doing a more sophisticated calculation in that it's reusing points in the stencil calculation and things like that. And I could actually express a lot of this very easily in Chapel. But a lot of the ugliness out here, actually, I will point out, is just the fact that I've ended up having to use things like local access to step out and not sort of have the Chapel distributions run a slow access to the array elements and jump straight to the array elements out here. And I suspect this is an optimization that one could immediately get inside of Chapel. So this at least gives you a flavor of why I like Chapel out here. I'll make another point here is the fact that I can do these, people can do convolutions, and people can write really fast convolution algorithms for these things. But a lot of times, I end up with convolutions where the convolution kernel varies with position, and I have to recalculate that. That's much harder to write down a simple algorithm in something like Python and say, here's a 27-point stencil, go ahead and do this convolution very fast, because it's optimized around the fact that the 27-point stencil doesn't change. A lot of these optimizations use that fact as well, but the previous code doesn't, and I could imagine taking this previous code and allowing the stencil to vary. And that's not a hypothetical example. The reason I started thinking about these multigrid algorithms was, in particular, I had a stencil that varied with position, and that's what prevented me from doing this all with FFTs. The first way you would do this all is, of course, with an FFT, which would be much, much faster than any of these things. Okay, let me say a few things about, more about Chapel. One of the things that's really important for me is that it can interoperate with other code. And in particular, it has to interoperate with existing C code. There's just large amounts of C code that exist. I'm not going to rewrite any of this in Chapel. And so it has to be able to do this. And in some sense, this is what is responsible for the success of Python, at least in astronomy, which is people wrote wrappers to existing C code and leveraged all of the existing code that exists out here. A lot of these interfaces are very, very domain specific to be of general interest. They're useful to me. They may be useful to a friend of mine. They're not useful to the community at large. And so they really don't need to be general chapel packages. But that means that it has to be very, very easy for me to wrap one of these things very quickly. So I don't want to spend hours trying to wrap it. If I was going to spend hours and hours trying to wrap these things, I would just go write it in C or C++ because it's faster, it's native, I don't have to worry about any issues. I think Chapel is a very compelling C story here, and I'll give 2 examples out of the 3 that I've looked at. FFTW, GSL, the GNU Scientific Library, and MPI. I'll talk about the GNU Scientific Library and MPI. I think an interesting question is there a compelling C++ story out here? Is there simple ways to at least do the simple wrapping to C++? So the GNU Scientific Library, if you haven't played with this is sort of my go-to box for I need a special function that I don't know how to code up, or I don't want to check that I coded it up right, or it's not in the standard math library. I need random interpolation. I need random numbers and distributions. I need to integrate functions and things like that. It's a large package. I'm never going to rewrite it. It's very, very useful to be able to get at this. The Chapel external block support really saved me here because we didn't have to update any of these things. And this is really thanks to Michael Ferguson, who fixed, I think, the few remaining issues in 1.13 out here. And so now, for me, using GSL within Chapel, and this is useful because any code that I have, if I want to do something complicated like do an integration, I just need special functions. Any interface into GSL involves writing code like this, which is basically do hash includes of the same headers that I would write in C. So I'd have to write exactly the same amount of code in C to use special function support or integrations, or get at constants to use the random number generator, and then I get the C API basically comes through. Now it's not completely smooth. I have to worry about things like C pointer twos if I'm passing things that I'm passing by a pointer. It doesn't switch to it doesn't use references out here, it goes to pointers. So you've got to do C pointer twos to references. But here's an example where you sort of call into the special function error function argument. Picked a bad argument, one here. Error functions are ones that exist in lots of other things. You could do array functions or whatever function you imagined here that you didn't feel like coding up. But you could immediately call in, if you look up how GSL defines the interface to the error function, it's a single element that it takes and you write out the answer. There's a version where you say, give me the error function, but also give me an estimate of the error on the estimate that you made out here. And so now you tell me the number, and because this is C, it can't return 2 variables, so you have to send it a pointer. And so now it gets a pointer out here, and you write out the pointer out there. And you can also do things like print what error message came out, and it was all okay, and things like that. It just all works. There is a rough edge. This would not be a talk if I didn't point out from the rough edges. Callbacks into Chapel are rough edges here. If I want to integrate a function, I've got to do a little bit more work because there's no way of passing a function pointer back to C in some clean way. So I can work around it, and so this was code that I wrote, which convinced myself that I could work around it when I needed to. But this is uglier than you would like it to be. You would love it to just be able to pass a Chapel function to C, saying that it knew how to deal with things. Let me say a little bit about Chapel and MPI, and my motivation for thinking about this. A large number of sort of scientific and numerical packages are built of MPI, and I'll argue the Chapel, in whatever form it ends up in, has to live in a world where it's going to interoperate with MPI. MPI is not going to go away. These packages are not going to go away, and Chapel is going to have to live with that out here. I came to MPI not because of this, though. I came to MPI because when I started playing around with Chapel, I started writing single locale programs, and those were great. And then you said, okay, I'm going to take some embarrassingly parallel program. I'm going to compile in multi-locale mode, and boy, it's going to run so many times faster. And that didn't quite work that way. You say, I'm going to run something, and boy, it ran slow, and then it ran in the single locale case, and you say, okay, what happened out here? You realize there are overheads with dealing with the fact that you've got to deal with, Chapel doesn't know that you've not done any communication, it's protecting itself out here. And so if you're a new user, this is a big hit, and you'd like a way around it, because you knew how to do this with very simple MPI. And so my approach here was to say, let me use Chapel and use Chapel plus MPI, much like use OpenMP plus MPI out here. I can also look up things, like if I know I'm doing some very simple operation that someone's done before. I can look up exactly what that parallel pattern looks like in MPI. I could just code that in. I don't have to sort of figure out how I would do that in Chapel out here. So I tried to do this, and I started off, the first version I did, I would sort of put pieces together by hand. And this is painful when you start thinking about all of the MPI routines that exist. And so what I ended up demonstrating is, it turns out that Chapel's interfaces is nice enough that you can mostly auto-generate most of this wrapper with a simple Python script. And by a simple Python script, I mean it's maybe about 50 lines of Python. And I'm not, as I said, go back to my original statement, I'm not a programmer, and I can figure out exactly how to wrap all of this and basically auto-generate most of it. You have to fix a few things, but only a few things out here. This is currently in master, and if you want to play around with it, please do. It's designed for Chapel in single locale mode, but hopefully one can extend it to Chapel in multi-locale mode, since GasNet itself already allows for MPI interoperability. And how might you use it? Well, here's hello Chapel in MPI. You do a use MPI, and if you want to use the CAPI, which is the only thing that really exists, you say use CAMPI. That pulls everything into the namespace. And you can do things like hello, hello world thing. It defines two module level variables on rank and size, because every MPI routine that I've ever written always first queries what the rank and size of that MPI communicator is. You can do things like MPI barriers, but just to prove that you can do more complicated things, here's a ring communicator. These are just standard demonstrations of how MPI works, but you can do sort of asynchronous sends and receives. You can do wait alls out here. You can get pass and buffers. The buffers go in as references. You have to send in the reference to the first element. You can't just send in the reference to the array, because that's just, I didn't have a better way of doing it out here, but otherwise it just sends in references. You will see no C pointer twos in any of this, so you rarely have to go down to that level of calling. And you can basically write MPI code. It looks like MPI code, it's because it's calling the CMPI routines out here. And you can do more complicated things just to prove that I did most of the MPI wrapper. The only things that didn't get wrapped were the pieces that required callbacks. There are a few MPI 1.1 routines that are callback routines, and since there's no way to do callbacks in Chapel and C right now, I decided I didn't have to wrap those. But you can build your own communicators. And the codes that I've written have all used that. I've got two more things to talk a little bit about as I've been using Chapel. One is interactive Chapel. As I said, the challenge often for me is not implementation, but what to implement. And part of that requires trial and error. I want to try out things. And this is someplace where sort of the Python, Mathematica, MATLAB, that class of languages, that story is a very, very nice story. They tell it's very easy to try out things. And I look around all my Python friends in Jupyter Notebook, they're all doing everything in these Jupyter Notebooks where they've got tracks of everything, and you can go fiddle around with things that are going on and make plots and dynamically change things. And Mathematica did this as well many, many years ago. And so I think Chapel would, at least from my perspective, be great to have a nice interactivity story out here. And I can imagine a few different versions of this. One version that I've seen and used a little bit is Cling, which is CERN's implementation of a C++ REPL based off the technology in Clang and LLVM. But let me make a different argument, which is that an interactivity story doesn't have to be pure Chapel. For instance, a strong Python interface would be wonderful as well, because I can now leverage Chapel to do all of the things that are slow in Python, but I get to use all of the Python ecosystem to deal with all of the things that I don't have a wrapper for Chapel right now. I can start playing around with those immediately. And this is what a lot of people use Python in anyway. They're interfacing to C, and I'd assert that most Python programmers would rather program in Chapel than in C, although I can't prove that because there's no data point I have on this. And so you can maybe ease people into Chapel and get access to all of the Python ecosystem and sort of be able to write real codes out here. The other piece where I've hit where Chapel programming, I have to say, has not been fun, is tooling. Debugging a Chapel program takes me back to sort of debugging with print statements scattered all around my code and sort of saying print here and print there and rerun. Profiling is somewhat nightmarish for someone like me, because I run a profiler and then I get all of the C calls, and I then have to look at the C code and try to figure out, and then go to lines, CPP lines, and try to figure out where in the Chapel code that came from. Quite tedious. I'd love to just know where a program's spending most of its time in a semi-automated manner. without any line, manually putting in timer statements, but telling me, so for instance, what it's at a line level or a function level. Another pain point is that the compiler is slow. So I'm not telling you anyone here anything that they don't already know. I would love to have fixed, but the compiler is slow, and error messages come out one at a time. So I fix something and then I recompile, wait till it compiles the world again and recompile again. And every time around I'm sort of recompiling all of my modules. It's all building everything all from scratch, and so there's no immediate reuse out here. The other piece that I find missing, and there's starting to be some bits in the current master for this, are chapel idioms. It's very easy for me to write chapel code like I would write C code, but clearly that's not necessarily the best way to do it. And it's hard to sometimes immediately figure out what those better idioms are. If I want to do a stencil operation, for instance, it'd be nice to know where those are. It would also be nice to know which idioms are currently slow and which idioms and what are the ways of getting around those when I need to go around this. So I'd argue maybe it's time for a chapel cookbook for the standard sorts of patterns you get in scientific programming. Can we have a chapel cookbook out here? All right, so here are my final thoughts. I'll end here. Chapel's lots of fun to use. I advertised my talk by saying I'll tell you what would stop me from writing chapel. And I think with 1.14, I have all of the various bits that I need to write chapel code, if I was the only person writing chapel code. And I think a year ago, that would not be true. The sentence got truncated, but a year ago, that was not true. I do miss interactivity, I do miss tooling, and I miss having a compiler that goes very, very quick, but that goes fast. I must say that all my interactions with everyone in the chapel team have been great, and that's sort of been the only reason I think that I've stuck with it and not said, I'm going to go back and just write a language that someone else has solved all the problems with. So that's been, they've been wonderfully responsible, so thanks for that. And thanks for listening. I'll take any questions.
You mean responsible after that first 9-month lag, right? Or 6 months. Questions for Nikhil?
So I wonder if are you planning to get on like the Xeon 5 processor, maybe GPUs? If you have, are you going to test parallel?
I would love to be able to, and this is one of the reasons I'm still in, that chapel keeps intriguing me. So the machines that we use, the machines at NERSC, and so the next generation machine is going to be a nice landing machine. And if chapel eases my getting those machines working at better than where I'm currently at, without sort of rewriting all of my code, that would be a wonderful aspect. So yes, no, I think the hope is that chapel will take away at least some of the pain at porting those for someone like me, where again I'm willing to say I'm not running at peak. I have taken a hit, but I'm using most of the machine. I'm not running on one core out of 32. Right? So absolutely, I think that I think is a very, very compelling case for chapel. And I think it's one way. I think things like Python will be behind. So I think having a good story early on means that people might be able to jump ship. Thanks.
Other questions?
So you had a MPI module and a CMPI module. So did you envision something differently for the MPI modules?
Yes. Michael had on my pull request, there was a comment that said, one of Michael's comments were, it would be great if we didn't have to write CMPI calls in chapel, because we know a lot more about the array we're passing in. The answer is yes, it would be wonderful to do that. I have no idea how to structure such a what those calls would look like, which calls you would want to wrap. There's a whole bunch of different ways to do it. And I figured get the CMPI version out and see whether people use it. And if people use it and have particular use cases, then we can start making that more complicated. The only current bits that are in there it computes world rank and world size, so I don't have to do it. It does the MPI initialization, so I don't have to do that. Currently, you still have to call MPI finalize, although Michael pointed out in the pull request there's a way around that one too. I just haven't implemented it and tested it out, so that you never have to do all of those bits. So you can just do that. But otherwise, currently there's nothing else in there. But it seemed like a clean way of, and this is what we did with FFTW, it seemed like a clean way of separating out the CMPI stuff from the MPI stuff. certainly for particular calls, if I was doing this and I found, it was getting painful to write the same MPI stuff, I was doing the same MPI, I would abstract out that, an MPI call and say, I'm always passing you a 3-dimensional array, figure out the bounds, send all of that information across, and make sure that works. And so in specific cases, it's very easy to do. I just have no idea what that general API should look like. And it didn't seem like a problem I wanted to solve.
I think another example we talked about was, in MPI, you're always saying send, these are MPI doubles or MPI ints or whatever, and that's the kind of stuff in Chapel, like, you could just write a generic version that queried the thing and figured that out and passed that in for you, right? That was something else we had talked about.
Right, that's right. And I just figured the simpler route here was wrap everything so that someone can't say we don't have a particular function wrapped. If you can wrap everything, and then let someone else figure out what that
Use
is.
a Python script to do that?
There was a simple Python script to do that. 90% of the way if you just want something quick. If you want something a little bit more permanent, or you don't want to recompile everything, or you don't want to run LLVMs backend out here, then taking that Python script or using a version of it and cleaning it up means you can generally have an automated way of making most of the wrapper. If you get most of the wrapper, you can always fix the small cases.
Great. Well, thank you very much, Dan. Thanks.